In 1985, the cement division of California Portland Cement Company completed installation of a 30-megawatt cogeneration system located in Colton, California. The project includes waste heat recovery from 2 existing cement kilns and 1 coal-fired circulating fluidized bed combustion boiler. Electrical power generated by the project satisfies the electrical needs of the entire cement plant and provides for sale of excess electricity to the local utility, Southern California Edison. This video presents an overview of the important aspects of the project. Hello, my name's Hank Campbell, and I'm pleased to present this interesting project that our company completed in the 1980s. Escalating electric power costs during the 1970s were making cement products less and less competitive with foreign suppliers. As a consequence, the cement division of California Portland Cement Company undertook an energy self-sufficiency project to reduce total energy costs. The project was begun in 1979 by studying the possibilities and feasibility of recovering waste heat from 2 cement kilns. The initial concept was to use this free energy to offset some of the plant energy needs by converting the waste heat into electrical power. After proving this concept to be feasible and economically viable, it seemed evident the thought process should be taken one step further. That is, looking at the overall plant energy needs for the cement plant to determine the most feasible long-range approach to serving the energy requirements. With making the plant totally energy self-sufficient was then studied. A key decision was the type of fuel to be used for generation of additional energy and its long-term price and availability. Because California Portland Cement utilized coal as fuel for the cement kilns, and the price of coal on a BTU basis was roughly half that of oil or gas, the decision was not a hard one to make. Project economics clearly favored coal as the right fuel for generation of energy. When the decision was made to utilize coal as a fuel to raise steam for electrical power generation, the air pollution aspect was cause for much concern. 2 choices were available with regard to boiler design. The first choice was a conventional pulverized coal-fired boiler. The second was a relatively new concept in coal-fired boiler technology called fluidized bed combustion. Detailed investigation to determine which technology would best suit the project was undertaken. The pollution control aspect played a very key role in the final decision. A visit to an operational fluidized bed facility helped convince our engineers that the fluidized bed boiler would be the best choice for this project. The fluidized bed boiler was chosen and sized to provide enough steam to generate electrical power such that when combined with waste heat recovery steam, the total plant electrical needs would be satisfied. Since there is a difference between average plant electrical needs and peak plant electrical needs, there will be periods when excess energy is generated. This excess energy will be sold to Southern California Edison for general public consumption. The cogeneration and coal-fired boiler facilities were integrated into the existing plant, which remained operational throughout construction. It was extremely critical that planning of the installation be precise. Over 900 drawings were required for construction of the project, and approximately 50 detailed purchase specifications were prepared for equipment and material. A design to permit the sequenced construction of a waste heat boiler and bypass ducting enabled cement kiln outage to be limited for 4 weeks. Planning for the shutdown phase of the project included prefabrication of all large ductwork and refractory lining of cyclone separators prior to shutdown. In 1982, construction was begun on the project, and contractors all moved on site and began the installation process. Gases which discharge from the rotary cement kilns are contaminated with a significant amount of fine particulate matter which become entrained in the gases. The plant utilizes a baghouse to remove this dust so the emissions would comply with federal, state, and local air quality regulations. Prior to the addition of waste heat recovery, a significant amount of cooling air was added at the kiln end housing to reduce the temperature of the hot gases to approximately 400 degrees Fahrenheit. This was done to increase the life of the glass bags in the baghouse. In the cogeneration mode, the addition of cooling air is discontinued and the now hot combustion products are diverted through the waste heat boiler. Because kiln exhaust gases leaving the kiln will no longer be cooled with air, gas temperature will increase to approximately 1200 degrees Fahrenheit. For this reason, it was necessary to replace the existing multi-clone dust separators at the kiln discharge with new refractory-lined cyclonic separators. The new cyclonic separators remove up to 70% of the dust, which is then recycled to the kiln through a conveyor transport system. Leaving the cyclonic separators, the hot flue gas flows to the waste heat boiler and then to an economizer, which heats incoming boiler feed water for the new waste heat boilers. The exhaust gas is then boosted by a variable speed fan into the existing fabric filter bag houses prior to being discharged to the atmosphere. The system retains the flexibility to bypass the waste heat boilers if necessary while still keeping the cement kilns in operation. Before the project was undertaken, the kiln-induced draft fan required 1,200 horsepower to handle the large amounts of cooling air necessary to reduce the kiln exhaust gas temperature. Eliminating this cool air will reduce the induced draft fan power requirements by nearly 62%. As a means to enable the waste heat boiler to be bypassed during shutdown, a cooling air damper was installed in the bypass ductwork. When the waste heat boiler is isolated by shut-off dampers, the kiln-induced draft fan horsepower will increase to the previous 1,200 horsepower. This change from approximately 450 horsepower to accommodate by a new variable speed induced draft fan installed on the kiln to allow both modes of operation. Circulating fluidized bed boiler components are comprised of the combustion chamber, 2 hot cyclone separators, 2 superheater banks, an economizer, air heater, and fabric filter. The cement kilns use coal for fuel, and the existing coal handling and coal storage is adequate to handle the new circulating fluidized bed coal needs. Prepared coal is fed from a 4-hour surge hopper to the loop seals by drag link conveyors. Each conveyor has 2 discharge openings located above rotary feed valves which seal against the boiler pressure. Final steam conditions produced by the boiler is 650 psig pressure and 825 degree Fahrenheit temperature. Steam output from the boiler is 172,000 pounds per hour. The fluidized bed combustion system provides a combustion process which utilizes limestone as an SO2 sorbent. The limestone is fed into the combustion chamber where it combines with SO2 to form calcium sulfate, which is then discharged with other solid ash components. The ash material containing reacted and unreacted limestone is discharged from the combustion chamber into an ash storage silo. From storage, the ash is fed into the cement plant raw mix blending process. The use of this ash in the raw mix blending process eliminates the costly problem of ash disposal, which normally represents a major project expenditure. Steam generated at the waste heat and coal-fired boilers is transferred by pipeline to the power generation facilities. Steam turbine-driven power generation units convert the steam energy to electrical energy. Steam is condensed into water and returned to the boilers where the heat cycle is repeated. Cooling towers and cooling water circulating pumps are used for condensing steam from the turbines. Engineers recommended for cost reduction the purchase and use of reconditioned steam turbine generation equipment. 2 15-megawatt units were located at a utility in Maryland, purchased and moved to California, where a complete reconditioning of the units was undertaken. Turbine generation equipment included steam surface condensers, 3-stage feed water condensate heating system, and auxiliary equipment such as an air ejectors and generator air coolers. Reconditioning of the equipment included retube of the steam surface condensers. The generator synchronizing switchgear, generator voltage regulation, and brushless excitation equipment were purchased new so that state-of-the-art control would be necessary. Water treating equipment is installed adjacent to the turbine generation facilities to satisfy the high-quality water demands of the boiler plant. The water reuse concept is another innovative aspect of this project. Water used in the cement plant is primarily for non-polluting uses. This water, after a small amount of heat is added, is usually discharged into an open area and allowed to evaporate. The cogeneration project reclaims this once used water and passes it through a settling basin where solids are removed. The water is then used for cooling tower water makeup. The boiler water lost through blowdown is replaced with demineralized water produced in a mixed bed multi-train demineralizer. This water then contains less than 5 parts per million total dissolved solids. A 100,000 gallon demineralized water surge tank with transfer pumps provides water in the event the plant water system is disrupted. Entrained air in the condensate is removed in the deaerator vessel. An oxygen scavenger is injected into the storage area, polished off any traces of oxygen. A neutralizing agent and corrosion inhibitor are injected into the boiler feed water downstream of the takeoff to the attemperators. Wastewater containing environmentally benign solid and chemicals waste from the cogeneration facility, such as cooling tower and boiler discharge, will be reused in the present cement plant dust slurry process and therefore does not represent a waste disposal problem. Major modifications were necessary to integrate the 30 megawatt power generation system into the existing cement plant. The cement plant is served by dual 66 kV feeders from Southern California Edison Company into an existing substation where voltage is transferred to 12 kV before distribution into the cement plant. New metering and protection was added to the existing substation facilities to meet utility interface requirements and standards. The new plant system is designed for total flexibility of power distribution under any condition. Under normal conditions, the electrical power generated is used to supply cement plant needs, and excess is sold to the utility. In the event that one or both generators are not available, the utility will supply the required electricity. A new 12 kV plant load center was installed to accommodate the difficult task of interfacing the new turbine generators, cement plant, and utility. Switchgear installed at the load center permits control of load flow, distribution, and is the focal point for synchronization of the turbine generators. The new cogeneration plant is controlled and monitored through a microprocessor-based distributed control system, which is located in a new cogeneration plant control room. The MBDCS is capable of full process and instrument analog control, generating of alarms and historical data, and ladder diagram type digital control. 5 major plant subsystems are monitored and are controlled through this system. Number 1, the turbine generators. Number 2, water treatment. Number 3, electrical switchgear. Number 4, the circulating fluidized bed boiler. Number 5, the waste heat boilers. We are very pleased to announce that Power Magazine selected this project as winner of the Environmental Protection Award. In 1985, the plant was started up and is successfully operating, complying with all of the air quality aspects imposed by the Southern California Emissions Control. Thank you for watching the video, and we hope you enjoyed it.